Dun dun dun, dun dun dun, dun dun dun, dun dun dun. Trying to get the distortion off that. There we go. Hello, everyone. So first off, I'm not going to use cameras when I'm talking. I just do not like seeing my face up there. I'll do some background images for now, and we'll find other things. Pearson has been having some issues. I have fixed the practice exam and the real exam. I've moved the due dates out until Sunday, Sunday evening on the Chapter 3 exam. And if Pearson continues to have problems, I'll move it again. That said, what was the other two things? Oh, I have had questions on some of the word problems, and I've been recording videos for those. I've been having sound issues, so those recordings will be placed online today. That's my big goal today, is to get everyone that has asked a question to get a video up for it and have those videos shared for everyone. So what I'm doing right now, and I'll come over here and show you the web browsers. So there's, hey look, there's the live stream inside of the live stream inside of the live stream. Yeah, that'll get a bit confusing, but let me come over here and into Blackboard. And so Blackboard, I've been running announcements, and so the first announcement is the lecture times. Are we doing basically four recordings of the lecture material? I'll be doing the Tuesday lecture as if the day class was meeting at the time of the day class, both Tuesday and Thursday. I'll also be doing the same material on the Thursday evening class, which is kind of split into two, about halfway through there, take a short break and come back to it. And this is to let anyone that might need to adjust their schedules have the ability to sit in on either lecture. Now, note I'm using the words, I am recording the lecture. I do use the chat feature here as a way of interacting on it. I know the interaction, well, it's been close to a classroom. In fact, I think actually more people are asking questions in chat than they will in a classroom. So I was about to say it's not quite the same as a classroom. I think what I'm missing here is facial expressions. I can sometimes see when I say something and it falls flat. But in general, using the chat and the live lecture gives us some interaction. We can figure out when things aren't working. Like we didn't have a pointer on the slides. I've changed my slide settings, and now I should have a pen function that lets me write on the slides, which we didn't have before. So as I come here to the slides, I now have this pen function, so I can underline words and do things with the slide that we were having problems with the graphics the other day. So by having the interaction, it can help fix things much more quickly than it would if I recorded these and then had to analyze everything individually. Alright, so that's the first thing, is on the lecture times themselves. Let me get to my browser here. The second part is I'm going to put a page up here that's going to collect all the lectures together and put some links together for them. I started doing this in my other classes, and I find it works fairly okay. And it's just with this particular class, I have to copy things into 4 places. The other thing is when you go into YouTube, I will have a direct link to this, which is my MWCC classes. It's a playlist, and then in all the videos I put in there. What I'm going to do is I'm going to make a playlist for each class. so that they'll be closer to get to, and that way you can jump right into things. If you miss a lecture, you'll get the lecture there. So I'm working on reorganizing this content here, so that the material is there. So those are the things that I'm focusing on today, and I will put a page up in Blackboard that will have quick links to all the information. Any of the live links still activate, so the live link from Thursday, let's see what was Thursday numerically, where did it go, is here. We had, and so my thing was off a bit there, but, and there's the live link from Thursday coming across and still playing. It also keeps track of the chat off on the side, so you can see the questions. If I remember correctly, it does replay the chat, so if anything, you can see the questions as they come up. So it tries to preserve as much of the interaction as possible. Alright, and so that's what I have administratively right now. Let me get back to here and go through what we're looking at today. Today we're going to look at graphs in a little more detail for particular types of functions. We kind of saw even and odd functions, and we're now going to look at different models of being, is it linear, is it quadratic, is it cubic, is it quartic, is it quintic? And we've already discussed those pieces. We're going to look at a little bit of the details that come out of them, and then we're going to get into the meat of this chapter, which is breaking apart polynomials into lesser polynomials, so that we can really focus on making solutions out of them. And I'll use the word, we solve solutions. We call those the roots, or the zeros, or the solutions. And those three words can be used interchangeably. And the zeros were the things that we were finding with our quadratics, and we'll continue to hunt for. So, again, a polynomial function can be of any degree n, and it has this really long definition where you have a leading coefficient and a constant, and you have coefficients that match up for each power of x. Any of those numbers can be different, and they work their way across. A lot of our focus will be on the leading coefficient and the constant. They help us determine a lot of different things coming out. The key is we call the function of degree n, or whatever the highest power is, and we write them in descending order by power. So you start with the highest power and its coefficient, and you continue to write every lower power. The only ones we don't write are when the coefficient is 0. The 0 multiplies it out. Now, we looked at the extrema, the max and minima, in the first section, and one was a max or minima. We're going to look at them also as they're called, when they're called turning points. And turning point is whenever it changes from increasing to decreasing, or from decreasing to increasing. So in this function here, this is a local maximum, and it's also the turning point. It is increasing. Sorry, the dog is right outside of the office, and she decided now would be a time to have a drink. I think she's better now. So the local maximum, she has been wondering what I'm doing over here at the corner of the computer. It does, I think, change her routine. So this function is increasing. It gets to the turning point. It turns and starts decreasing. Continues decreasing until it gets to another turning point and starts increasing again. And turning points will be local min or max, or even absolute min or max. When you hit a minimum or maximum, you have to turn around. The nature of a minimum or maximum is the function was moving or traveling in one particular direction, and you reach the largest or smallest value you're going to reach, and you have to change. So when we're saying turning points, we're describing the same thing as a min or a max that we described before. And in this case, they're local because the function continues off. In fact, this function particularly starts at negative infinity and runs off to positive infinity. So it has no absolute minimum or maximum. I can always make a bigger number if I get larger values or smaller values of x. And you'll see we'll talk about this. We'll say this is big end behavior. We talk about how the function happens when the absolute value of x gets really big as we push it towards infinity. So either we're going towards negative infinity or positive infinity. We see the behavior of the function in general as it comes across. If it's always increasing on either big end, then in the function n is even. If it increases and then decreases, n is odd. And so I know this function n is odd because it has both infinities in it. And that's something we will see as we do loads of these. Chapter 4 looks at a lot of polynomials, and I'll try to point out these behaviors that happen. In fact, I would say because it has two turning points, n is at least n to the third for this polynomial. Whatever degree of the polynomial is, you will have that many turning points. Minus 1. So a degree 3 polynomial will have 2 turning points. And so n behavior is a description of what happens to the graph as either x becomes very large or x becomes very small. We say the n behavior of the graph tends towards negative infinity or positive infinity, which is what I was describing here, the big behavior or the and I call it big end. Infinity is big. And if we're going to positive or negative infinity. And so something does happen as we get towards infinity, even if we haven't reached infinity yet. The function starts getting more and more predictable. And so we looked at all these functions. So the book is reviewing what we talked about. I kind of combined them all in the section for section 1. And I kind of preluded a lot of these. So I'm going to go a little fast for this and point out some things going through. But this is all what we looked at in the last lecture with a little detail. And so if we have a function that has, we can really write this as f of x equals a, if I don't put the sub-zero in, x to the 0. If we're going to keep our polynomial form, but anything to the 0 power is 1, and multiplying anything by 1 is itself. So we get that constant, what the coefficient was is a constant. And we call these constant functions, constant polynomial functions. And they're a horizontal line. They do not turn. In fact, they're never increasing or decreasing. So we go back to our definition here, that a turning point occurs whenever it changes from increasing or decreasing. This function is never increasing or decreasing. It's constantly the same value, hence its name. So it will not have any maximum or minima. Everywhere along the line is its max and min value. It's that one value, right? And so in the case of the first one here, right, y equals f of x, well, this function is actually f of x equals 4. Whatever I put in for x, I still get a 4 out of it. Whoops. And this function here is f of x equals 1, 2, 3, negative 3. Whatever I put in for x, I put in negative 4 for x, I still get negative 3 out of it. Put in 4 for x, I still get negative 3 out of it. My function is always constantly the same number. Alright, whoops, I didn't mean to draw the line there, but that's okay. A linear polynomial function, well, whoops, it is not letting me undo the lines. Let's see. Erase all link on slide. Ah, there we go. That's better. A linear polynomial function is of the first degree. We can say that x is to the first power. And this is a graph of a line that's not vertical or horizontal. It intercepts the x-axis in one place, but note there's no turning points. It's always either increasing or decreasing. And what they're saying is if a is greater than 0, it tends towards infinity and negative infinity. And if a is less than 0, it tends in the opposite direction. What I like to say is if a is greater than 0, it's always increasing. Sorry, my pen motion is causing it to flip if I press too hard. And in this case, I'm going to rewrite the form up above it. Decreasing. That we saw this as mx plus b. And so this first coefficient is the slope, if we want to relate it to things we had done before. And let's look at that. Look at what that means. This function here has a slope that is positive because it's always increasing. And I remember kind of standing off on the side of the board and drawing like a circle of all the different slopes and what happens to them. And the larger the slope, the steeper it gets. And the negative slopes, the larger the slope, the steeper it gets, but are coming down. And so here I can say a sub 1 is greater than 0, and no matter where I'm at on this function, if I move in the positive x direction, or if I move towards infinity, the function itself moves towards infinity. Right? If I'm here and I move in this direction, if I move in the positive direction, my y values get larger and larger and larger. Here, a sub 1, or my slope, is negative. I think I might just use the mouse instead of my pen. And as I think it's just touching the paper if I don't. As x goes towards infinity, the function itself goes towards negative infinity. It's always getting smaller. A decreasing function, always getting smaller. And linear polynomials are really nice for us because they've got this point here, which we're going to call a solution, where it intercepts the x-axis, or the root. Okay, and linear polynomials have one root and one root only. And that's going to be a key, one of our keys. Now here's our friend the quadratic, which we're still just working our things through on. Make it thinner. I want to change pen color. I don't know if anyone has ever heard me. I hate red as a color. So I'm going to change that. Now notice our highest power of x is 2. And so we call this a degree 2 polynomial. And if a is greater than 0, we say it is a upward graph. Right? The parabola smiles. Something about so I turned off the click function on my pen, but something about the slide software is putting it back on. So I'm going to use a normal mouse here for now. So parabola opening upward was when the leading coefficient was positive. When the leading coefficient is negative, it was downwards. That meant that the turning point for these were a minimum, and a turning point for these were a maximum. Now, it can intercept the x-axis in 0, 1, or 2 places, and it has exactly one turning point, which we called the vertex. If a was greater than 0, then its big N behavior was to go off towards positive infinity. And if a was less than 0, its big N behavior was to go off towards negative infinity. So let's look at these. So here I have a vertex on the y-axis. I do not have any x-intercepts. It does not cross. If I were to actually solve this function, I would get imaginary solutions, because my solutions are where it crosses the x-axis. If I continue to go out towards positive infinity, this continues to rise towards positive infinity. If I go out towards negative infinity, this still rises towards negative infinity. And so even functions, or quadratic functions in particular, will go towards one direction. Right? This function has one solution. If I were to solve this quadratically, I would get the answer x equals -2 using the quadratic formula. It would be repeated twice. We call this a repeated root, and we'll see that more as we move through here. It also has a positive a value. The vertex is a minimum. And as I go towards positive infinity, this goes off towards a positive infinity. And as I go off towards negative infinity, this goes off towards negative infinity. This last function, a is negative, so it's frowning. Its vertex is a maximum, and I have 2 solutions that are equal distance from its axis of symmetry. There we get this axis of symmetry drawing on here. And they have these 2 solutions, or 2 roots. So if I were to solve this quadratically, I would get an answer of what appears to be 1 and 4. -1 and 4, roughly, would be my 2 answers from the quadratic equation for this. Now notice, we have worked with quadratics. We have worked with linear equations. We've solved for the x variable when the function equals 0. We've looked at turning points. We've looked at slopes. Every other polynomial will contain pieces of the lower functions in them. So we're going to look at the behavior of the higher degree polynomials, and our job will be to break them down into quadratics or linears. And so we have a cubic function in which the leading coefficient, or not the leading coefficient, the highest power of x is to the 3rd degree. So we can say, hey, a cubic's a 3rd degree polynomial. It can cross the x-axis 1, 2, or 3 times. It has to cross the x-axis. Functions with odd degrees, because they end up in negative infinity and positive infinity on either side, have to cross somewhere. Now, it may cross multiple times, but it has to cross at least once. Okay, if we compare that, I'm going to go back to the quadratic here. To the quadratic, it doesn't have to touch the x-axis, right? We had this example here where it doesn't have to touch the x-axis. But cubic functions have to touch at least once, because on one side they're going to go off to negative infinity, on the other side they go off to positive infinity. And if you're going from negative infinity to positive infinity, somewhere in the middle, you have to go through 0. You have to switch from being negative to positive. So these odd highest powers of n have to cross the x-axis at least once. Well, that's what a line did. So it has a behavior at the end. If the leading coefficient is positive, then it will start negative and raise towards the positive n. And if the leading coefficient is negative, it'll start positive and work its way towards the negative. And let's look at that. So this third degree polynomial has 2 turning points, because at the most it can have 2 turning points. Whoops, let me erase that. Alright, so you swapped sets of problems here, I see. So there are the 2 local mins and max. Comes with here. Notice that a must be negative because it's starting out at negative infinity. It comes down, crosses the x-axis once, turns, crosses it again, hits here, and crosses it again. But it starts at positive infinity on its big N behavior, and it ends on negative infinity on its big N behavior. Now this function, the middle one, starts at negative infinity, has 1 turning point right in the middle here, and this is a unique turning point because it changes the shape. We'll call it a point of inflection, where the shape changes. It's not really a min or max, it's still always increasing, and then heads off towards positive infinity. So notice a cubic function has to start at one infinity and end at the other one. And once it does that, it has to cross the x-axis somewhere. And this one has, again, 2 distinct turning points. Looks, the longer I hold it down, the more it makes a line. Let me see if I can fix that. Now I will continue to play and make the pen better. Let me just get rid of the ink here for now. So we again start at negative infinity. We cross the x-axis. We hit a turning point. We come back. We just touch the x-axis with another turning point, and we head off to positive infinity. And again, the large-scale behavior. I start at one infinity, and I work my way towards the other infinity. And if I have to go from a negative infinity to a positive infinity at least once in the middle, I'm going to cross the x-axis. And that's what those rules mean. A quartic polynomial is degree 4. It can have up to 4 times it crosses the x-intercept, the x-axis, and 3 turning points. So whatever the polynomial is, it can have up to 3 turning points, and it can have up to that many times that it crosses the x-axis. It, in general, mimics a quadratic. And that's what this behavior is saying here. So I'm going to go look at the function. So this is like a second degree function. I come down and then I shoot back up. So the A is positive and the answers are always positive. But this can come down, have a turning point here, there's one. Come back up, have another turning point, go down and shoot back out. Overall, I can imagine a parabola kind of hiding behind all this. It's big behavior. If I were to look from it very far away, it looks like a parabola. And this fourth power equation comes up has a point of inflection there, hits a turning point, and goes down. So a must be negative. The leading coefficient must be negative for this polynomial function because it starts negative and ends negative as tends towards infinity. And the same for this quadratic. It starts negative and tends towards negative. It's got 3 distinct turning points in it, and it crosses the x-axis. These don't have to cross the x-axis. This whole thing could be shifted up. And we could continue going on. Quintic functions. Quintics have the same behavior in the large scope as lines and cubic. So now I'm going a little bit quicker. And we look at, hey, it does the same thing a cubic function does. It starts at negative infinity, goes to positive infinity. So I know the leading coefficient is positive. I get at the most 4 turning points. 1, 2, 3, 4. This function starts at negative infinity, goes to positive infinity for its big N behavior. So I know the leading coefficient is positive. Let's see if it'll let me write. So here the leading coefficient is greater than 0. Here the leading coefficient is greater than 0. Because I start at negative infinity and I go off to positive infinity. Here, the leading coefficient is less than 0. Because I start at positive infinity and I go off to negative infinity. And so this big N behavior relates very much to the power of the function and if the power of the function is even or odd. The number of times it crosses the x-intercept is really important because when we cross the x-intercept, our y value or our value of the function is 0. So when we say the word x-intercept, we're also saying that the function itself equals 0 at that point. And we call these things x-intercepts, solutions, or roots. And we'll even use the word zeros at some point because, and they all mean the same thing. At the most, a polynomial function will have its degree of intercepts. So if I have a constant function, it never intercepts the x-axis. A constant function is of degree 0. It never intercepts the x-axis. There are no x-intercepts. A linear function is of degree 1, x to the first power. It crosses the x-axis once. And because it's odd, it has to cross at least once. So lines always have an x-intercept. The parabolas and the quadratic functions that we were looking at have at the most 2 points where they cross the x-axis. So let me come over here and show that. Change this, scroll up, clean my Blackboard. All right. So a quadratic function can have 2 x-intercepts. Just one, where it just touches. Let me put my arrows up here. Or none. These are all valid quadratic functions. They're all a greater than 0 because they're smiley faces. They're positive and smiley faces. But they have a different amount of x-intercepts. But at the most, there's no way I can take a quadratic function and get it to cross the x-axis again. It would need to turn one more time to cross the x-axis again, and adding that additional turning point would make it cubic. And so that's where the second part of this comes into play, where at the most it has one less turning point than its degree, which is I've been trying to point out as we've done this. So if you're an even degree, you always end up where your A value is. If you're an odd degree, you start and you end where the A value is. So you start at the opposite end at the A. Because this is when we were looking at the linear, the cubic, and the quintic. I said, hey, I start negative and I end up positive if A is positive. I start positive and end up negative if A is negative. Even degree functions always end up where their leading coefficient is. Remember, this A is that leading coefficient, this number in front of the polynomials. And so we have this big N behavior that happens based off that leading coefficient. And we can think of it as this, and I'll show you a trick for remembering big N behavior. And I'm just going to look at two polynomials here. Let me switch over here, come over to the blackboard. All right. So if I have a polynomial, and I'll do degree 6. And I'll even put some big coefficients in it just to smack home the point I want to do. Alright, so as my values for x increase, the whole system of numbers changes here. But something really neat happens as I get closer to infinity. For example, if I put 100 in for x, that's 100. This is 100 squared, which is considerably larger. This is 100 cubed. This is 100 to the 4th. This is 100 to the 5th. This is 100 to the 6th. This is getting bigger. This gets bigger considerably faster than any of the other powers. And so subtracting 100 off from the end here doesn't really make a difference, right? Think of it as money. If I had $1, right, and I plugged it into this function, these subtractions would really, really hurt. Right? Subtracting 100 times x to the 4th and subtracting 100, and if this was $1, I'd be losing money on this whole thing. But if I were to put in $100 for this, well, this 100 to the 6th, what does that become? That becomes $1 billion. And so $1 billion, I subtract 100 from it, that's not going to make much of a difference. If I were to change this to $1 trillion, this all of a sudden continues to go up, and that 100 on the end doesn't matter as much. And so the smaller powers don't change the function as much as the leading term does. And so the leading coefficient decides the big N behavior. Because as I increase this number, if I put $1 trillion here, 1 trillion, which is 10 to the 15th, right? If I take that to the 6th power, that's going to be incredibly bigger than 1 times 10 to the 15th to the 5th power, right? My rule of exponents says this would be 10 to the 90th power, and this would be 10 to the 75th power. So as this gets big, this leading term just gets bigger than everything else, to the point where the other values don't matter. Well, the point where it doesn't matter is at infinity. So as I get to infinity, this thing takes over. And so all these rules we're talking about, all these things we're listing, are because that first term, when our x gets extremely big, will make all the other terms look really small. And so that's why we talk about N behavior of what happens. All the other terms get small comparison to what's happening with the big N behavior. Okay. And so if we look at a graph here, we can go, hey, there's 1, 2, 3, 4 turning points. It intercepts the x-axis 1, 2, 3, 4 times. All right, so there's 1, 2, 3, 4 turning points. 4 turning points and 1, 2, 3, 4 x-intercepts. Now, is the leading coefficient A positive or negative? Well, we look where A ends, our big behavior, and it's negative. So we know, that A is less than 0. It's negative. And we have 4 turning points, so this has to be at least degree 5. And that's what we have there. And so that's how these functions help us look through. That's how these functions work through as they touch the axis, and how we can help find out what are happening. Okay, I'm going to skip the examples here. Yeah, I want to go, sorry, there's one on a calculator, one I do want to skip. I want to look at the end behavior itself. Now, when we have a function here, we want to write it in descending order. Now, this is written in reverse order, and you'll see this a lot of times when the coefficient is negative. And I'm going to write this behavior around so that we can see what's happening. So let me just, sorry, my switching key is, there we go. I just switched between the different windows. It's not as easy as a mouse click here, and the key's been going through. So let me rewrite this function. So I have f of x equals 2 plus 3 of x. Yeah. 2 plus 3 of x, f of x. It's not writing. There we go, f of x equals 2 plus 3 of x minus 3x squared minus 2x cubed. Make sure that's what we had here. Trying to remember all the coefficients. Yes. Now again, I said we should really write our functions in descending order. And so the book's going to say, hey, look for the highest one, and that's your leading coefficient. But I would prefer, and it just helps us start thinking about the things we need to think about in order, is if we write them with the powers of x descending and the sign of the coefficient to tell us what's happening. So if we want to think about its big N behavior, all we need to worry about is that part of the function. So the first thing I look at is its degree 3, because x is to the 3rd power. That means, in general, I don't know where on the graph, but in general, A is going to determine where I end up. And so it's negative, so it's going to end up here. And at the most, it can have 2 turning points. So it's going to start somewhere. And so this function is going to look like this, or it's going to look like this, where it has just a point of inflection on it. And so by being a 3rd degree function, I have these options of what it's going to look like. And one of our jobs is going to be trying to find these roots. But just this first term lets me know that I'm starting at positive infinity, ending at negative infinity, and I'm going to have behavior that's going to be like this, either of these. And that's what the degree and the leading term of a function will let us do. All right, so that is what the graphs of the polynomials do. This is the behavior. And I've through this whole course, I've always wanted to focus that we're graphing things so we can describe things visually. And we started with lines telling us what the rate of change was, how functions were moving, were they increasing or decreasing. And then we used parabolas to see that point of change that they might have, and when the function might be becoming different. And we're going to continue to look at this behavior. The core concept of the line is still underneath it all. When is it increasing or decreasing? That's really what the line gave us. Then in the parabola, or the quadratic equations, give us our turning point with the vertex. Any higher polynomial can be made up of chunks of different of those things. And those chunks come from multiplication. And so notice we're going to look at how can we divide polynomials, because we want to break them apart. And so we did this early on with the idea of factoring. So if and I'm going to show this. If I know I cross the x-axis at 4 and -2, I don't know the rest of the shape of my polynomial or my quadratic right now, but I know I cross at -2 and 4. Well, crossing the x-axis meant that f of x equals 0. So what happens here is I have something where if I put in -2 for x, I get 0. And if I put in 4 for x, I get 0. So I have x plus 2 equals 0. Well, what happens if I put in -2 for x? I get 0. So where did this come from? Oh, wait. These are my x values. So I could say x equals -2 and x equals 4. And if we notice, this is where I end when I solved a parabola. This was my end point. So we're going backwards. We're going to reverse this process. So I'm going to put all of my numbers on one side. So I add 2 to each side. And I get x plus 2 and x minus 4. And if I have some relationship that are connecting these 2 points, something had to happen that they were together. Right now I've got 2 solutions. Now, in doing quadratics, we said, hey, these could be factors. We factored these out, or we used the quadratic equation. We did something to get through them. So if they're factors, we're relying on the idea that a times b equals 0. So if this is my a and this is my b, well, that equals 0, and that equals 0. 0 times 0 will give me 0. So I'll put my 2 factors together, and I'll FOIL. And this was the function that defines this. Now, depending on where other points of data are, I have some coefficient out front that determines my a value. But I have the base polynomial. So that's going from our answers to our polynomial. We spent time learning how to factor this down into these terms. We want to be able to do the same thing now if x is cubed, x is to the fourth, and x is to the fifth. Because putting these things together as a multiplication, this factoring will rely on divisions. And so that's why we're going to talk about dividing polynomials. We're going to look at the mathematical operation of dividing polynomials. We're going to look at different methods for doing it. And then we're going to look at how we can find what we need to divide by for our polynomials. So we're going to start just dividing. We're going to divide. We're going to be given what to divide by. We're going to get simpler and simpler terms from it. Eventually, we're going to have a polynomial of any degree, and we're going to have to figure out what we need to divide by to get our answers or solutions. So we're using all the little bits and pieces we used with a line, with a quadratic, and we're going to put it all together for any degree. And I've warned you, and many times when we looked at something on the board, I would say, hey, we're going to do this for any degree. We're going to be able to break them down into these littler things, smaller parts, component parts. And so we're going to talk about the division here. Now we will only get through probably the first 2-3 sections of this. We're going to do synthetic division at the last half of the week, and the remainder theorem definitely all in one class on its own. The remainder theorem leads into our finding rational roots, and it's the key. But first, we're going to learn to divide polynomials. And so we want to divide a polynomial by a monomial. So I'm going to take this here, and I'm going to do it on the blackboard. I find the slide versions of these are not as enjoyable as my babbling. No, I'm going to look at the component parts. So let me write this here. I have 6x cubed minus 3x squared plus 2. And that is all over 2x squared. All right, let's switch over here. So I have rewritten this here, 6x cubed minus 3x squared plus 2. If we kind of reverse the idea of what happened when we had a common denominator. So I'm going to think in blue. Well, I'll think in green. If I had A over B plus C over B, I could write everything as a common denominator. These individual terms came from the two numerators. This is why we focused a lot on getting common denominators. I'd say early on when we were looking at the properties of real numbers, I should have shown a proof on how this comes from. So I know in my developmental math class and in my 097 we look at how this works from the property of real numbers. But once we have a common denominator, we can bring the numerators across. Well, this is saying I have a common denominator and I have these linked numerators. In fact, I have terms that aren't like each other. So I can reverse this process. I could say, hey, this term, let's see, I'll make that the yellow term. I'll make this the green term, and I'll make the 2 the purple term. And so the yellow term was its own thing. And the green term was its own thing. And the purple term was its own thing. If I want to go forward, these all have the same common denominator. I can use my rule of common denominator in fractions to blend these together, and I would get this. But I'm dividing. I want to go backwards. I want to simplify this. So notice this term is a monomial. What I am dividing by has no additions or subtractions in it. Oh, is the audio looping? Okay. What is happening here? All right. All right, so we got an audio glitch. You hear silence now. Can you hear me now? Yeah, I was quiet while I was typing. All right, can we have an audio check? Yep, okay. And you should hear me talk shortly, Jim. There's about a 20-30 second delay. And if you came into the stream a little late, you might be on a longer delay. All right, good. All right. Yay, audio check. Sorry about that. It happens sometimes, and sometimes there might be a local echo coming through. What I'm going to do here, okay, come back to my graph. Okay. Woohoo! Thanks. We can treat each of these terms the same. Or the same as independent beings, I guess would be the better way of talking about it. So here, 6 divided by 2 is 3. Then x cubed divided by x squared is x. I'm simplifying each fractional term on its own. 3 divided by 2 is 3 halves. Right? X squared over x squared is 1, so I'm left with an x half, 3 halves on its own. 2 divided by 2 is 1. And I'm left with x squared down below. And that is the answer to my division. When the downstairs is a monomial, I break it into its individual terms. Alright. I'm going to look at another monomial here before going on to a non-monomial. Dividing by monomials. Let's get another one. Scroll down. So if my function, if I'm looking at division of 3x to the 4th minus 2x squared minus 1 divided by the monomial 3x cubed. Yeah, that static noise in the background is the tea kettle. As I am right off of the kitchen here, and we have the family working their way out towards their day. So someone has put the tea kettle on. So the static you're hearing is the tea kettle going through. Yes, there will be some background noise. Occasionally you'll hear the squeaky door that I need to oil. Alright, so we're dividing by a monomial so we can break it apart into individual terms. Again, the key is there are no additions and subtractions in the denominator. So I can look at it term by term of the numerator, sharing that denominator. When learning new things like this, where it's a deconstruction from a rule, always double check that you could go back. That, hey, I have a common denominator, so I can blend the numerators. And if I take 3x to the fourth minus 2x squared minus 1, do I get back up there? And I do. Right. A lot of our mathematical properties are reversible. Right. The ability to distribute can be reversed. In fact, we're kind of doing that reverse distribution here. This division is taking out something that would have been distributed into one of our terms. So, 3's cancel, and the x cubed leaves me 1x upstairs. This gives me 2/3 out front. The x squared is going to cancel all but one of these downstairs. And this one is as easy as it gets. Okay, nothing more I can do there. If I wanted to check myself, I could multiply this whole thing by 6x cubed, or 3x cubed. Sorry, 3x cubed. And if I were to distribute that to each term here, I would work my way back up. And so it is a reversible process. Division is the reverse of multiplication. And our ability to divide by a monomial is able to work us backwards and forwards, which will be nice when we get things like this. All of these have a common factor of 3x, so I can divide by 3x. Right? Divide this by 3x. Whoops. Divide by 3x, showing you the why we start our divisions. And so this would give me x squared plus x plus 1. Well, that 3x would have been one factor, so I'm going to rewrite this equation as 3x times x squared plus x plus 1. And I now have the ability to say, hey, 3x equals 0. That's one of my solutions. And x squared plus x plus 1 equals 0. That'll give me my other solutions. That's where this is all going, is that we can take these larger polynomials and break them down. If our last term in the polynomial still has x in it and we don't have a constant, we're going to be able to pull at least a monomial out. Because I have at least whatever that last term is working its way through. And so that's the thing to look for. If this was 3x cubed plus 3x squared plus 3x plus 5, I couldn't do this. I wouldn't get a nice clean term out on the end. And that's going to be part of our job, is determining when we can't do it. And so monomials are what lets us do the greatest common factor. All right. Well, I can divide by monomials. Well, I can also divide by another polynomial. And here, when we're going to look at dividing by polynomials, we're going to borrow an idea from long division. And we're going to start doing long division. So I'm going to grab our polynomial out here, and we're going to come back up to the blackboard here. First thing I want to look at is I need to save this. I ran out of blackboard space. Alright, we'll close this. Reopen it as blank. I'm trying to get a key shortcut that will do all of these steps for me. I haven't written the script for it yet. Sorry about that. Alright, so I'm going to borrow the idea from long division. So if I take 2,600, or no, 26,100, and divide it by 36. Without using a calculator, and the algorithm we're looking for here is really dependent on not having the numerical answer, but having a process. And so this becomes the value that we want to divide by. We're actually dividing by the 30s, right? Each one has a place value. And so we look at each place value here, and we work in descending place, order of descending place values. And so we take our number and we say, hey, can I divide that into my 20,000s place? Well, 36 does not divide into 2 evenly. So we tend not to write a 0 up above, but we just move over. And we look at 36 and we say, hey, can you divide into 26 evenly? And you can't. And so we get over to the hundreds place and we go, well, hey, 36 goes into 261. Well, how many times does it go into it? 8. So 7 times, I believe. 7 times 6 is 2. Carry my 4. All right. So this goes in 7 times. I am on the blackboard and it didn't switch over. I was erasing the blackboard, and when it erased, it switched you back to the other screen. Let me restart here. Thank you for that, Leica. Oops, there we go. All right, so I will repeat on the blackboard. Thank you for that heads up. And just to double check, I'm looking at my stream now. Yes, the blackboard is showing. Okay. All right, so the algorithm we're going to look at is the algorithm of long division, and it's dependent on place values. And so we're taking 36, and we're seeing if it can divide into each individual place value. So 36 can't divide into the 10,000s place because 36 does not divide into 2 as a whole integer. 36 also does not divide into 26, but it does divide into 261 7 times. So proceed our way over until we find the first place that this divides into. We put the number of times it divides into, and we multiply that back out. So 2, here your 4, 7 times 3 is 21, so 25. And we subtract. 2 gives me 9, and so I have 9 left over. I bring down the 0 because I am now moving into my next place. I'm moving into the tens place, and 36 goes into that twice. So 2 times 6 is 12. Now notice I am focusing on my new number. This algorithm starts with up here. Once I get the subtraction, my new number that I'm looking at, that I'm now doing my division with, is here. And so 2 times 36 is 72. I subtract. So I get 8 and 1. I bring down my 0. And 36 goes in that 5 times. 5 times 6 is 0. Carry my 3. And I have a remainder of 0. And so 2,600, or 26,100 divided by 36 is equal to 725. Now I've got it. We can do this on a calculator. That's fine. But the algorithm of focusing on place values and subtracting out to get the next number we work on is what's going to be borrowed very, very heavily in polynomial division. And we can treat the different variables of x as if they are place values. So the division I want to do here is going to be a polynomial, and we're going to borrow this algorithm from numerics. So I have 2x cubed minus 3x squared minus 11x plus 7, and I'm going to divide all of that by x minus 3. Now the idea we're going to borrow is that each of these terms is a place value. The individual degree of the variables are the place values. So I'm going to rewrite this in the form of a long division. I'm going to be dividing by x minus 3, and I'll put my division bar out here. So we want to see how many times this goes into each of these by place value. So our focus will be, we start with our leading terms. So this is my leading term here, and this is my leading term here. So I want to know how many times 2x cubed is divided by x. I look at just my leading terms. So step 1, look at leading terms. And if I do this division, this isn't as bad as numbers. I don't have to guess my way up. I can, hey, this x is going to cancel this. This will give me 2x squared. So this part, this leading term, goes in 2x squared times. So I'll write up here 2x squared. So I divide leading terms. I'm just going to put LD for leading terms, and we'll write it above. Notice I'm lining up my x squared with my x squared. I'm treating the degree of each term as its place value. And I have 3, 2, 1, and 0 for my x's. Now I multiply. I'm going to jump up a board here. Okay. When I had the 7, I multiplied it by 36 to get the 252. So here I'm going to take the 2x squared and I'm going to multiply it by the x minus 3. So 2x squared times x minus 3. So the 2x squared comes to the first point. I get 2x cubed minus 6x squared. Well, that's what I want to write here. I get 2x cubed minus 6x squared. If I have done, and so we'll say write this below. And I write it below lining up the powers of x. Right? My cubes are cubed. Now if I did this right, always, if I do this first leading term, whatever I multiply should be exactly the same on that first term. And so we subtract. And again, I'm going to scroll up a board here. If we were in class, I'd be pointing from the left board to the middle board. I subtracted these two things to get the 9. So when I subtract these, well, I'm going to show my subtraction by changing my signs. Okay? So when we subtract, we change signs. 2x cubed minus 2x cubed is 0. These will always cancel out. If I did this right, I get the same thing, and they cancel out. These terms, 6x squared and minus 3x, gives me 3x squared. Let me go back, change color, back to where I was, sorry. And so pull down next term and repeat. This is a repetitive process. As these 8 steps go over, you look at the leading terms, you divide the leading terms, you write it above on the bar here, sorry. You multiply, you write the result of your multiplication here, you subtract. And now I pull down my next term, and I have a new leading term. And so now I'm ready to repeat with this being my starting point. So I'm going to break down these rules here, and then we're going to go through this step by step. But this is what it borrows from long division with numbers. We are doing it now with variables, and we're letting the variable power hold individual places. So let me change coloration here. So our rules: divide leading terms. Write the answer. Yes, Jen, I will scroll back up in a second. I'm going to write this down and then come back. I'm kind of summarizing what's up above. Write the answer above. Multiply the answer by the divisor. Write this result below. Subtract. Pull down next term. And repeat. And the note I'm going to put on this is always line up powers of x. So this is the algorithm here. I'm going to leave this up for a minute, and then I'm going to go back up to the other problem, and we'll just keep running through these steps and repeating through them. We're going to look at this with when we have a remainder and when we don't have a remainder, and where different divisions come out. All right, and so we will have a remainder here, and then we'll check some others. Make sure you have these referenced somewhere. I'm going to keep talking about these. See this, whereas in class I'd keep looking at your pencils to see if you're still writing or not. But for here, I'll just watch the clock tick a little bit. Alright, so I'm going to continue doing that on this, but I'm going to get my eraser out and erase these things off on the side here. My eraser is a true eraser, but I can fix this in a second. Oh, maybe not. I'll fix this in a second. You guys bear with me here. Okay, this happens in class all the time where I'm stuck on the blackboard. There we go. That's a better eraser. That's the eraser I wanted. Actually, it looks like my eraser in class. There we go. Alright. Yes, cats do want to learn too. I think they learn better than us. Alright, so I have done my first step here. I looked at my leading terms, which was the 2x cubed and the x. I divided them and I got 2x squared. I put that up above and I multiplied, which gave me 2x cubed minus 6x, which I put here. And I subtracted. Now I repeat. This is my new leading term. So I'm going to not do the leading terms off on the side. I'm going to look at this. I'm doing 3x squared divided by x. Well, 3 is positive, so that's going to give me a positive 3, because 3 divided by 1 is 3. And x squared divided by x is x. Right? Right? So let's remultiply 3x times, yes, I get the same thing. Now my next step is to multiply. So I'm going to take 3x times x minus 3. And I'll do it term by term. So 3x times x is 3x squared. 3x times negative 3 is negative 9x. Now again, if I did this right, and I'm saying that not as a, oh no, we're going to do this wrong, right? It's a place we double check. These first terms should be exactly the same. This algorithm makes sure these first terms are the same. So my next step is to subtract. So when I subtract, I change my signs, which turns this into an addition. These will cancel out. And negative 11x and 9x gives me negative 2x. I bring down my next term, positive 7, and I repeat. So I'm going to do a quick jump down here. All right, I divided my leading terms. I wrote the answer above. I multiplied. I wrote this result below. I subtracted. I pulled down the next term, and I repeated. I looked at my new leading term. I wrote the answer above.
I multiplied, I wrote the result below, I subtracted, I pulled down my next term, and that's where I'm at right now. So I've pulled down the 7. And so my new leading term is negative 2x. And so negative 2x divided by x. Well, the negative 2 is going to stay, right? The negative 2 is going to stay because negative 2x over x, well, the x's cancel. So I'm left with just the lowly negative 2. Now I'm going to multiply. Negative 2x times x is negative 2x. And negative 2 times negative 3 is positive 6. And I'm going to subtract. Again, if I've done this right, these two first terms should be the same. And so I'll change my signs. And that leaves me with, whoops, a remainder of 1. Now, remainders are neat things in dividing up polynomials because it's saying underneath it all, I can say this is my answer with a remainder of 1. And remainders, we can also write it as 1 over whatever we had here. And so you'll find I will tend to write them like this unless I need the remainder. For a lot of what we're going to do first, we're going to write these answers with our remainder out to the side, because we'll be dealing with something called the remainder theorem coming up. I'm not sure I'm going to reply to that last comment, just to say that the answer is that's probably truth for everything, it is easier. Anyway, I'll leave it as that. All right, so this is most of today's talk. We've got about 20 minutes left. What I'll do here is we'll start back up with dividing polynomials. Dividing polynomials, we're going to look at loads of different variations we can see on these. What I wanted to focus on was the algorithm is the same as the long division algorithm. I do find that modern tendency in school to use calculators, a lot of people don't have the long division algorithm down. So I want to really focus on these rules. We divide the leading terms, write the answer above, multiply the answer back out by the divisor. What we get from that, we write down below, we subtract, pull down the next term, and repeat. And we repeat until we've cleared the ones place. Always line up the powers of x. And I'll start off next time with where that gets weird, where like what happens if you have x cubed minus x, but you're missing the x squared? What should you do with that? And other different things to go through. So I'll plug that all up. All right. Any questions on any of this? I will fix the audio on the videos I have there. I'll put some subdivisions on it. I hope you saw the note. I'm recording 4 lectures during the week. There are 2 lectures of material, Tuesdays and Thursdays. I record it Tuesday and Thursday, and then I also record those 2 things again Thursday evenings. That's so schedules have changed, right? People's watching cats, watching children are different than what they were pre not having face-to-face meetings. And so because of that, I'm not requiring people to be in during class time. But having questions helps. It helps me adjust things, especially having questions on the material. Questions on the recording type stuff, the switching back and forth on screens, I don't do when I record the stuff on my own. I actually can watch what I'm doing. It's a little bit easier. But please ask questions on the material. Please send me email on the material. What I'm doing today, because questions have come up on the stuff for Chapter 3, is I'm recording examples of all the word problems. I'm going to have those up that are on the practice exam. Again, I know there's been problems with Pearson, so I'll modify the due dates. And with Jen saying with how long she is working, you're not required to be here for a live lecture. I'm not doing attendance. I will post the links to the lectures. You can watch them at your leisure if you can't make a given time. But if you want to be here and interact, that's wonderful too. So I'm recording the word problems from the Chapter 3 practice exam. We're looking at taking the online exam by the end of the week, but I'm going to continue talking about Chapter 4. All the due dates for Chapter 4 really start next week. I will have the homework for the first 3 sections up today. If you're comfortable with the Chapter 3 or done with the exam, you want to start looking at that homework. And what I should do here, all right, I'm going to try to figure out, I think I'll just end this. I'll just put the goat head picture on it. Reminds me of a Rolling Stone album cover. And then I'll just say, hey, if you have any questions, otherwise you can bow out of chat and I'll end the stream shortly. Be safe, be well.